This video, we're fitting a linear model in terms of a line of best fit to model a scatter plot of data. We can create linear models based on real sets of data, which are not always perfectly straight. So in this graph below, you can see the blue dots represent some real data points, and you can see that that red line that's going through them is an approximation of a linear model that will fit that data. That line is called the line of best fit. It's also known as a least squares regression line as we move through this course. So the reason why we have these lines is so that we can best model some practical data, because practical data will not always be perfectly straight. This way, if we have a linear model that fits it, we can use the line or the equation generated from the line to help make predictions about the practical scenario. So let's start by having a look at a question. So we start off firstly by finding two clear points on the line and stating their coordinates. So in this problem here, we have a line that's already fit to the data. In your questions in your text, you will always have the line already there. You will just be creating the equation to match the line, and then you'll be using it to make some interpretations in terms of the context. So this one here, we can clearly see the line has been fit for us, and we are told that there are 2 points on the line. Now, those points on the line do not have to be actual data points that was originally in the sample of data. Okay, we are just fitting the line to it, and then from there we are saying, oh yeah, this would be one of the coordinates on that line, and this would be as well. They don't have to actually belong to the original set of data. I hope that makes sense. Okay, we find the model that fits it by following the steps that we have been following up until now. So we start by getting the two coordinates. We'll label them x1, y1, x2, y2, and then we're going to use those values and substitute them into our equation to find the gradient. We then again find the y-intercept by using the steps that we have in previous exercises. So depending on what the question has, sometimes you can find the y-intercept by just reading it off the graph. If you have a graph and you know the y-intercept, i.e. the value of y when x is 0, then you can directly read that y-intercept off the graph. If you don't have the graph, you can do it by substituting a point in to solve C. Now, I'm not going to repeat those steps right now. Just remember that they were shown in 6E. So if you want to go back and look at that, you can. We will go over it a little bit more in this lesson as well. So you might want to hold off, and if you still don't understand this point, then go back and have a look at 6E. Alternatively, you could be completing steps 2 and 3 using your Casio. Again, that was taught in exercise 6F. If you want to go back and have a look at that, you can. But again, we will go briefly over it in this lesson. Okay, so these are all steps that you have taken in previous exercises. We are just now applying it to a line of best fit. Okay, let's keep going. So this example has a graph of 6 students, English marks versus their maths marks. So these little data points here show each individual student's marks. Let's do an example, this little X here. That particular student there, that would mean that they got 50% for their maths mark, and then reading it off the Y, they would have got just over 40 for their English mark. Okay, so that's what these points here mean. So in this question, a linear model in terms of this line here has been fit to the data. We want to try and match an equation to this line. Okay, so we do that following the steps that we followed previously, which was 1, highlight 2 points that are on the line. And again, they do not have to be the actual data points from the data. They just need to be 2 points that we can clearly see are on this line. Okay, any sets of coordinates on this line you can use. Okay, so in this example, we've highlighted 60-60 and 40-30. Okay, we're going to use these 2 points and the techniques used previously in order to find the equation for this line. So we start off by step 1, labeling these points x1, y1 and x2, y2. Then we're going to substitute those into our gradient equation, which is m equals y2 take y1 on x2 take x1. So in this case, that will give us 60 take 30, because I got my 60 from here and my 30 from here. divided by 60 take 40, which was my x here and my other x here. Okay, once I solve this, it's giving me 30 over 20, which again, solving that gives me a 1.5. Okay, so there's my gradient. I want to know the whole equation. So the next step would be to write out my equation as y equals mx plus c. So I'll be writing y equals 1.5x plus c. Okay, just like that. Now, because we know it's English mark and maths mark are our x and our y, it would make good sense at the end as well to, instead of having an x here, you would actually write the word maths mark. And instead of writing a y here, you would write the words English mark. Okay. Before we do that though, we need to find our c value. Now, as per the previous part, we would be looking at the graph to see if we can find our c value, our y-intercept. At the moment, we can't see what that is. Okay, it's not showing up on the graph. So we need to now go and substitute a point into this. And again, this was taught on previous videos. We will go through it again briefly now though. So I'm choosing either one of these points, either 60-60 or 40-30. And we're going to substitute one of those into our x and our y values here. Okay. Do not worry which one you use. They are both going to give you the same answer as long as you're doing it correctly. All right. So let's go and do that. So I've either put into the equation. In this example, I am going to choose to sub in 60-60. Okay, so x is 60, so I've popped that into my x here. My y was 60 as well, so I've gone and put that into the y spot here. Okay, now that I've got these, it leaves me with C open and I can solve C. Okay, so let's continue solving this question. 60 equals 1.5 multiplied by 60 plus C. Calculating what this is here is going to give me 60 equals 90 plus C. Solving for C here would give me C as negative 30. Okay. Hence, my equation for this line here is going to be English mark equals 1.5 multiplied by maths mark, take away 30. Okay, because I've gone and substituted in these names instead of the X and the Y, and I've subbed in my M into my M and my C value into my C value. We could be using our calculators to do this as well. So just a quick reminder here on how to do that. You would go to your statistics function, then you would insert those coordinates into the lists. Okay, so list 1 is your X values and list 2 are the corresponding Y values. Then we go and hit the buttons to get us to this, which is calc, regression, linear reg. Hit OK, and you will get this little setup here. That's telling me my A value, which in this case, my A refers to my y-intercept, is negative 30, and my gradient is going to be 1.5, which is exactly what we got from before. So that gives us the same equation as before. Okay, so I've rewritten that here. The second part to this question is going to be using this model here to make a prediction. So that's the whole point of this. We have a model here that allows us to predict marks. If we are given the mark of one subject, we can make a prediction for the other. So this one asks us to use the equation to predict a student's English mark if their maths mark was 50%. So I know my maths mark is 50 and I want to know my English mark. So I take my equation here and I'm going to substitute 50 into that maths part there. Okay, just like so. Solving that would give me 45. So I can make the prediction that if someone had a maths mark of 50%, then their English mark would be 45% as per my line of best fit model. The last part of this is looking at the reliability of predictions. So if we are using these models in order to make predictions, some are reliable predictions and some are not reliable predictions. So let's have a look at what makes a prediction reliable. So if we have data to support an answer, then it's considered to be reliable. Okay, so if the data that we have and the data that we are predicting is within a similar range to each other, then we say that that's called interpolation. That is a reliable prediction. Okay, the prediction must be within the data range that we have in the question though. And I'll show you this on a graph in a minute. It makes a lot more sense when you see it on a graph. If our data point that we are trying to make the prediction for is outside of the set of data so it's beyond the data that we have, then we consider that to be an unreliable prediction, and we call that extrapolation. So if the prediction lies outside of our range of data that we have, that is not a reliable prediction, called extrapolation. You need to remember these two words here. They are really important. You'll often be asked on a test, is this a reliable prediction? And you need to be able to answer in terms of either one of these words. Yes, it is reliable because it's interpolation, or no, it's not because it's extrapolation. If that doesn't make sense yet, let's have a look at on a graph. So this one here, this was what we were looking at previously. We were looking at the maths mark of 50%, and we're making a prediction for English here. So was that a reliable prediction? Well, maths mark of 50%, let's go to our graph and have a look. 50% for maths is here, where my cursor is right now. If I follow that up, we can certainly see that is within the data range. We have data that supports this, okay? So if I was making a prediction that was outside of this range, then it wouldn't be reliable. But because this one here is certainly nestled within these data points, then it's certainly going to be reliable. So in this case, yes, it's a reliable prediction, and that is because it is within our data range. We have data that supports this range of this prediction, and hence we call that interpolation. Okay, and you can just say that word, interpolation. You don't have to write an essay as long as you've got that word written down. Okay, so let's have a look further up here. So any prediction that is made within this area here where our data lies, any prediction here is going to be reliable because we have data to support it. So if I asked in English, what's my English mark if my maths mark is 30? Is that going to be a reliable prediction? Yeah, maths mark of 30 here, it's within my data range. So it is a reliable prediction, and we call that interpolation. If I was asked to find the English mark if my maths result was 100, you can see 100 is over here. I don't have any data in this area that supports the answer, and so that would not be a reliable prediction, okay? So we still make the prediction, but it's not going to be terribly reliable. We call that extrapolation. All right. Lastly, you will have some questions in this section that look like this as well. And this essentially is getting you to think about interpreting your gradient. What does your linear model actually mean in terms of the data? So this one here, when the maths mark increases by 1%, what does the English mark increase by? Again, when you see this sort of language, my X increases by 1 something. What is my English mark increasing by? My Y. That means look at your gradient. Okay, that's telling me a 1.5 in this example tells me every one we go up in X, we're going up by in Y by whatever this value here is. So when my maths mark increases by 1%, my English mark is going to be increasing by 1.5. Okay, because again, think rise over run. All right, I think you've heard enough of me. Let's go and have a go at 3 questions. 6G, part 3.